Hello data managers, this is Mr. Dunbar speaking. Welcome to the last video for Activity 5 in Unit 5. We're going to start off by looking at question 5. This is a question we'll be able to get an answer by counting. We'll be able to figure out some of the probabilities, some of the events by counting. But in other cases we'll have to use permutations and combinations to get our answer. So let's take a look at the scenarios. If we roll 2 dice, what is the probability that we will roll a sum of 5? What is the probability we'll roll a sum of 7? And we've got a whole number of other possibilities. So let's take a look at the first of the examples. If we roll 2 dice, what is the probability that we are going to roll a sum of 5? So the answer, the short answer, is 1 in 9 or 4 in 36. Now, we can roll 5 in 4 ways. We can roll 1 and 4, 2 and 3, 3 and 2, 4 and 1. And you can see all of those will add up to 5. And that is the likelihood of the event of a sum of 5 being rolled. So one thing we need to observe is that the order is important. It matters whether we roll 1 on the first die and 4 on the second die, or vice versa. So, to get our final result, we first need to have the number of possibilities for that particular event, so the summation to 5. And we also have to have the total number of outcomes possible. Now, how do we do this? Well, we have 2 permutations here. So we've got the possibility of die 1 and the possibility of die 2, and combined they make 6 times 6, or 36 possibilities. Now let's take a look at that in terms of our permutation. So let's take a look at the math. We have our 2 dice. Each dice has 6 possibilities, and intuitively we understand that that gives us 36 possible permutations. Now, I'd like to remind you of the generic formula for permutation. N permute r equals n factorial over n minus r factorial. And then if we complete our math, we end up with a total of 36. But how does this look? Well, let's focus on one of these permutations. 6 permute 1. So how many ways can you arrange one object if you've got 6? Well, we've got our answer, 6 factorial divided by n minus r, which happens to be 5 factorial. So 6 factorial divided by 5 factorial. So that would be 6 times 5 times 4 times 3 times 2 times 1 divided by, and just for the sake of cleanliness, let's put a bracket around this, 5 times 4 times 3 times 2 times 1, and closing bracket. And you'll notice that when you divide these two numbers, you are left with 6. Because 5 times 4 times 3 times 2 times 1 divided by 5 times 4 times 3 times 2 times 1 will give you 1. So you've got 6 as your answer for 6 permute 1. So we end up with 6 permute 1 times 6 permute 1 equals 6 times 6 equals 36. One more thing you can do is complete a dice chart. This obviously works for simple problems, but not for complicated ones. So if you've got the sum of 2 dice, you could make this chart ranging from 2 all the way up to 12. So if you've got 2 1s or 2 6s, those are your 1 in 36 chance probability. Now if we roll 2 dice and we get a probability of rolling a sum of 7, we can use our dice chart and we can look at all the cells that end up with 7. So we have 1, 2, 3, 4, 5, and 6. So that gives us a 6 in 36 probability of rolling 7, and we simplify that to 1/6. Now, here's a question that can mess you up. If you roll 2 dice, what is the probability that you roll a sum of 10? Well, when we use our dice chart, we end up with 3 in 36, or 1 in 12 as our probability. So we can have 6 and 4, 5 and 5, and 4 and 6. Notice how we do not double up on the 5 and 5. And the reason for that is that if you roll 5 on the first dice and you roll 5 on the second dice, it's the exact same thing as rolling 5 on the first dice and 5 on the second dice. Whereas if you do 4 and 6 and 4, it's a different story. So if you were to list the possibilities, you might list 4, 6, 5, 5, 5, 5, 6, 4. You would erroneously double count your 5, 5. So this is an example where you have to pay attention, and in this case, the dice chart would be helpful. A slightly different question. What is the probability that you will roll doubles when you roll 2 dice? So the same number on both die. Well, let's take a look at our dice chart. We can roll 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, and 6, 6. So in this case, again, we have 6 possibilities. 6 out of 36 simplifies to 1 in 6 probability. What's the probability that we roll a number divisible by 4? So that would be 4, 8, and 12 in this scenario. So in this case, we have 9 numbers that are divisible by 4. 9 in 36 is 1 in 4, or a quarter. So the first attempt at this question meant we counted the numbers that were divisible by 4. Simple to do. Alternately, what we can do is break this problem into 3 separate cases and then use the rule of sum. So what we're dealing with is 3 different events. We're dealing with an event where the numbers sum to 4, they sum to 8, or they sum to 12. So we have to ask ourselves, what is the probability a number is divisible by 4? It equals the probability that we got event where the sum is 4, probability of event where the sum is 8, or probability of the event where the sum is 12. So 3 in 36 chance for a 4, 5 in 36 chance for a sum of 8, or 1 in 36 chance of a sum of 12. We add those together and we end up with a quarter again. So now let's look at a probability question that requires us to use combinations to find the answers. Well, in this case, we've got a cheerleading squad of 6. It has 5 girls and 1 boy. Now we're going to have a bunch of scenarios here where they line up on a field for a cheer, and what's the probability that, well, in the first case, the only boy is at the front of the line. So the only boy is at the front of the line. We've got 2 solutions available to us. We can use basic logic, and there's only one place that we want the boy to stand, and that is at the front. So out of 6 positions, he can only stand in one of them, so that's 1 in 6. Secondly, we can use permutations. The number of ways the boy can stand at the front of the line is going to equal, well, with the boy at the front, so that's one possibility, and then we arrange the remaining 5 players in the other positions. So 5 times 4 times 3 times 2 times 1, a regular factorial in this case. So 5 factorial. So we have 120 ways to line this group of students up with the boy at the front. The total number of ways of arranging these 6 people in a line is going to be the total number of possibilities, which is 6 factorial. 6 times 5 times 4 times 3 times 2 times 1. So the probability that the boy is first is going to equal the number of positions where the boy is first over the total number of possible positions. 120 divided by 720 is 1/6. Now, solution 1 is certainly simpler, but when you have more than one object, you are in all likelihood going to have to use permutations or combinations. So let's keep Sherry and Terry together in the next question. Now we have the probability of Sherry and Terry being together is equal to the total number of ways that Terry and Sherry can be together, n bracket s and t, all over the total number of outcomes. So again, we have to use our permutations and combinations. In this case, we have 5 objects. We've got the 4 other players, and we've got Sherry and Terry behaving as a group. So we have 5 blocks that we have to arrange. So 5 factorial. Then within that block for Sherry and Terry, there are 2 different ways to arrange it. So 2 factorial. So we got 5 factorial times 2 factorial, all over the total number of ways of arranging this group of 6 individuals, 6 factorial. So in this case we have 240 over 720 equals 1 in 3. So the probability that Sherry and Terry are together is 1 in 3. So let's look at a slightly different question. We've got 14 people running for 6 Senate positions. 3 of the 14 people are sisters. Each candidate is equally likely to be chosen. Okay, so we've established a few facts. Now, what is the probability that all 3 sisters will be on that committee of 6? So, we can apply counting principles in this case, since our events are equally likely. And the other thing that we have to think about is we're thinking of all 3 sisters being on this committee together. That's an AND proposition, which means we're multiplying rather than an OR proposition where we would be adding. So in this case, the probability that all 3 sisters appear on the committee is 3 choose 3, because we want all 3 sisters and we're choosing all 3 sisters. So how many different ways can we choose all 3 sisters? Well, it's 1. Then we have 3 positions remaining, and we have 11 more candidates remaining. So in that case, it's 3 choose 3 times 11 choose 3, and then we have to divide it by the total sample space. So the total number of possibilities, n bracket s, in which case you've got 14 individuals and you're choosing 6 of them. So that would be 14 choosing 6 for your divisor. So 1 times 165 divided by 3003 is 5 in 91, or 5.5%. So now let's take a look at the detailed explanation. So what I already said. Here we have the total number of possible samples, n bracket s, is 14 choose 6, which we saw up here. Oops. 14 choose 6. We've got 14 people, we need to choose 6 of them. Now, then we have to look at the subset where we've got event A. So how many different ways can we set up event A, which in this case is 3 sisters choosing all 3? So in that case, we're doing 3 choose 3. So we need to choose the 3 sisters and 3 others, which is why we multiplied the 2 combinations together. Remember how I mentioned we're dealing with an AND situation, which means we are applying the multiplication principle. Now, what's the probability that only 2 of the 3 sisters will be on the committee? So we change things ever so slightly. The probability that only 2 of the 3 sisters will be on the committee is 3 choose 2. We're choosing 2 of the 3 sisters. Now we have to remember that the 3rd sister will be eliminated from contention, which means that we still only have 11 other people that we're choosing from, and we're choosing 4 positions in this case. So in this case we've got 3 choose 2 times 11 choose 4, and then we divide it by our total number of possibilities, which still is 14 choose 6, and in this case we have a 1/3 probability, 30 in 91. So that's pretty good. 2 out of 3 sisters, we got a 1 in 3 chance of having 2 out of the 3 sisters represented on this committee of 6. And this has to be my favorite type of question. It is one that I see crop up in real life time and time again. I use this principle probably at least once a month, even if I'm not thinking about it. So what's the probability that at least one of the sisters will be on the committee? In this case, your result will be shockingly high, and that's one thing that people are often astounded by. So what is the probability that at least one of the 3 sisters will be on the committee? So in this case, I always reach for indirect reasoning. So what's the probability that at least one of the sisters is on the committee? Well, we've got 1 as our total probability, and we're going to subtract the probability that none of the sisters will end up on the committee. That's the easiest scenario to calculate. So in this case, we've got 1, that's 100%, subtract. How many ways can we choose 0 sisters? So 3 choose 0 times, how many ways can we choose 6 members from the remaining 11? So 11 choose 6. And then we divide it by the total number of possibilities. So in this case, we have 1 subtract 462 divided by 3003, and when we do the math, ta-da, we get 11 in 13. That is an incredibly high probability that at least one sister will be selected for this group of 6. By the way, that's 85%. So, the second solution is to look at individual cases, which can very rapidly become quite complicated. So what's the probability that we have at least one sister on this group of 6? Well, that is equal to the probability that you have one sister, or the probability that you've got 2 sisters, or the probability that you've got 3 sisters, which are summations, by the way. You add them together. And we set it up of 3 choose 1, you're choosing 1 sister, times 11 remaining people, and you're choosing 5 from the remaining 5 people from the remaining 11, divided by the total number of possibilities, plus 3 choose 2 sisters, 3 choose 3 sisters, and we sum that together, we get the same result. So in this case, indirect reasoning is much shorter, and I find that I use indirect reasoning when I'm doing things with probabilities very frequently.